please welcome Ingmar for his talk. Thank you. Boy, life is good. I got off just in time.
My name is Ingmar Pöse. I do not come from Australia. Sorry, that must have been wrong in my intro. I'm actually from Germany, so not that far away, but still far away enough. I'm going to talk about Ingress Point Detection. That's a project I did together with a couple of universities here in Germany and joint work with Stefan, Helge, and Oliver. So let's dive right in what this is all about. We do a lot of analysis for ISPs and a lot of network analysis. And one of the questions that keep coming up is, for example, service degradation. And you have a city and parts of the city have a service degradation for something. And we have absolutely no idea. I need to figure out what's going on. So the first question is it the subscribers themselves that have the service degradation? Is it somewhere near them? Is it coming from somewhere else? Are we actually looking at overloaded links somewhere? Do we have congestion on the links at any point in time? Do we have a problem with peering links, or is this an upstream problem that we're seeing? And maybe it is something else. So debugging these things is actually quite hard. Now, at that point, it's easy to figure out what IP addresses or what source and destination the traffic has that is affected. But it is really, really hard to figure out which path through the network this takes, because IP can't look backwards. It can only look forwards. So this is why we came up with Ingress Points and Ingress Point detections. I'm pretty sure we didn't come up with Ingress Points, but we did come up with the detection for them. So the very easy or well understood term for this is an Ingress Point is where the traffic enters the network. It is the first point that traffic touches a network of an operator. Doesn't matter where it goes. It doesn't matter if it terminates within the network or runs through the network. The point is the first time the traffic touches the network, that's what we see as an Ingress point. And the nice thing about that property, that feature, when you have an Ingress point, is that traffic from that point is only forwarded. And forwarded traffic can be followed. If we have traffic that moves forward, we can start looking at IGP and BGP in our analysis, because they also use the forward path. We can take into account routing policies. We can take into account traffic engineering that all follows forward. And of course, we can track behavior along the path and say, this is a reason, or this is not a reason on this. The design space that we are actually in here at the moment for the Ingress Point detection is we would like to know for possibly all traffic that is seen by a network, where that traffic enters the network based on the IP addresses or IP address ranges that it comes from. We want this to adapt automatically when changes happen in the Ingress Point. So if upstream changes something or if announcements change, we don't want to have manual intervention here. We want this to automatically update itself. We want to be able to keep a history. Now, of course, you can keep all of your traffic or all of your net flow or whatever you're using, but that's a huge amount of data. We want this in a concise form that lets us go back weeks or months if we want to and say, hey, at that point, this traffic most likely entered on that link. And lastly, we want this to be lightweight in terms of hardware and in terms of processing power. So that sounds like a little bit of a tall order, but I think we managed most of this. However, we do have a few limitations that we are looking at here. One of them is that we mainly focus on heavy traffic sources. I will get to that on the next slide. We cannot reason about Ingress points for traffic that we haven't seen. So if there's no traffic for a source, there's nothing we can do. We won't know about that. And unfortunately, if there's router-based balancing of traffic, we can't do that either. I'll get to the router-based balancing later, but It's routed, so when traffic is balanced between two different routers, we won't be able to detect an ingress point correctly. Okay, now the original idea when this whole ingress point detection started was about 8 to 10, maybe 12 years ago, when I was researching CDN ISP collaboration. So the idea here is that a source is sending some kind of traffic, either directly or it sends it indirectly. And we want to map the sources, so the CDN servers, clusters, data centers, whatever, to the users inside an ISP. And the main challenge that we had at that problem is, if the servers were on net, we could see where the ingress points are because then they're directly connected. But as soon as they're somewhere else on the internet, coming from official data centers, coming through peering links, coming through something, it is really hard to figure out where that traffic will enter the network. And that's how ingress point detection was actually born. You have just these multiple sources, multiple points where things can enter, and there is absolutely that back then there was no way of actually doing that automated and figuring this out. So what are the sources or what are the ingress links that are being used for different syncs inside the ISP's network? In order to figure this out, I want to go a little bit into the design challenges that we're facing, or that we were facing for this. First of all, in order to reason about where things enter the network, we need traffic monitoring on all border routers. For us, this meant we had thousands of border routers, thousands of links that we had to actually look at where traffic could potentially enter. And this is a huge amount of traffic. We are using sampled traffic information, but still, this is an avalanche of information that's rolling towards us and that we somehow need to make sense of. The second problem is, yeah, we can just look at every source destination pair and track that, but that doesn't scale very well. Tracking individual IP addresses either on the source or the destination side means that you have, in the case of IPv4, already 2 to the power of 64 combinations that you can potentially see. I know that it's way less, but it's enough to explode any kind of RAM, especially back then, to actually track this on a per IP level. So we needed something that scales a lot better than tracking individual IPs. But if we do that, the whole not tracking on an individual IP, we need to know which granularity do we need to track at. Is it /24 okay? Do we need /27, 28, 29? We didn't know. And so we decided to go with a solution that would try to figure this out by itself, rather than saying this is the granularity that we're going to track at. And then I already touched on this point before, ingress points change. So in this example that you can see here on the left, we have a couple of servers that have /25, /28, /24s, and they all come in somewhere differently. And they also might change links or get reconfigured if they're for any kind of reason. So we needed to be able to infer this dynamically, the granularity, something that is not done once and then we stick with it, but this needs to be continuously updated, continuously, and in line as the traffic comes in, figure out which granularity on what link, what traffic is ingressing. This slide is basically, no, you cannot use BGP for this. For one, if you remember the last slide, there were announcements in there that were smaller or bigger, depending on which side you're looking from, than a /24. So a /25, /28, you can't really announce on the internet or propagate through the internet. This gets even dicier if you use v6. But the main reason BGP is not an option here is that the announcements for BGP actually flow towards the source. which means what the source sees is the IP address of the customers or of the link that it runs through. But the traffic runs in the other direction. So the BGP announcements actually don't tell us where traffic comes from. They just tell us where we're announcing our own address space. And if we're looking at the address space of the servers, then we only know where to reach them. We have no idea where they're actually going to send the traffic. And so BGP as an option is completely out. We can't rely on BGP for this. Yes, BGP announcements point the wrong way. I just want to really point that out, that this is not something that should be used in this kind of analysis. Finally, the ingress points change often. I already touched on this, but in the traffic that we actually observed, 60% of our ingress points were stable for less than 1 hour. So there's no point in trying to be static here. We really need to go with a dynamic solution. The good thing is when we look at the traffic that the ingress points, once one was chosen, were actually fairly singular and fairly stable. So even though we see multiple ingress points, only one of them is usually carrying most of the traffic. And even though more BGP, more ingress points exist as a possible entry point, only one of the paths is actually carrying the traffic. And this is a nice thing because it allows us to actually pinpoint the ingress points much better, and it also alleviates us from the fact that the one thing that the ingress point detection can't do, which is router-based traffic balancing, actually it doesn't have to, because most of the traffic runs from a single ingress point, so it looks more like this rather than like this. Yeah, and so we wanted to detect the dominant ingress point. We wanted to figure out where the traffic comes in for certain sources where we don't even know how big they are. And with that, I'm done with the design aspects, and I'll go onto the actual system design. This is the system design is actually there's a two-stage approach here. For the IPD, but we need to remember we should not, cannot, will not use BGP as an input. We use flow protocols, so it says NetFlow here as input, which is not necessarily needed. You can also use other flow protocols, SFlow, JFlow, CFlow, NetStream, IPFix. They all work as long as they have source destination and you know where they were sampled on which interfaces. It works. The scale is we need to scale to thousands of routers. We need continuous monitoring. We need dynamic prefix aggregation. And in our scope is everything that is connected to the edge of the network, be this customers, be this peers, be this upstream, downstream links, anything that leaves and anything where traffic enters our network is in focus for us. And again, our goal is to figure out where the high traffic prefixes are and which are the dominant links where that traffic ingresses. With that, I'll come to the two-stage approach that we have. The stage one is basically deal with the avalanche of NetFlow or flow protocols. This is a lot, really a lot of traffic, and the only job of that stage is to collect it fast enough, to ingest it, and to prepare the data. There is no processing done. It really just builds the data structures, and that's it. Stage two is run regularly. I think we ran it every minute on the new data that came in from stage one. And that one classifies the ingress points, finds the dominant ingress points, updates the data structures, and so on and so forth. It is also responsible for then writing the current configuration of the ingress points to files or to a database, wherever you want to store it, so that they can be used by further down processes and or stored for being used at a later point in time. I've talked a lot about the theory of this. Let's do this in practice. So what is it that we're actually doing? Imagine we have a network here. This is a sync network, which means we have only subscribers. There's no traffic running through, but that doesn't really matter. The first assumption that we do is we know nothing about the internet, which means we classify the entire internet as a /0. Everything is on the same link. We have no idea. And the only thing that we say is, in order to make any kind of decision on the knowledge that we currently have, is we need at least 7, or in this case, 11 samples to do any kind of decision. So eventually traffic will come in, and it will come in on the different links. I've marked the links here with the different colors so that it's easier to see on the IP address range where things are hidden, where things are. And at some point after our first interval is over, let's say after a minute, we check what do we know. And at this point, we know that we do have enough samples. So we do have 11 samples. And we check if the networks, if the subnets that are one smaller, so the /1s, are only mapped onto one single link. No, they're not. Also note that as we move down, as we make the subnets smaller, so we're now at the /1s, the number of samples that are needed inside the individual subnets decreases. This makes sure that we always have sufficient information about a subnet, but don't need too much in order to be still able to get medium loaded links. So point being, we still don't know enough. We can't split any further, and nothing is actually matching here. So let's go further. Let's add a couple more more samples. So wait a little bit. After T2, we see that the left subnet has enough samples again, so we can split that again, and we can see that the left of the /2s now only has one single color. So we could technically classify that one with that color, so for that link, but it doesn't have enough samples yet. It needs at least 5 samples. It only has 3. So while this is a good candidate, we're not quite sure yet, and we go to T3. Go on. At this point, we have enough samples, and we say the entire range of the /2 over here, this is our prevalent ingress. Note that if you have address ranges in there that have never seen traffic but would actually belong to a different link, you won't see that. So this will only find the prevalent ingress on the traffic that is actually being seen. But I think that as someone who operates a network, traffic that you're not seeing is probably not that interesting for you. And the algorithm continues. The right /2 can't be attributed to an ingress, so it's split again. And at some point, samples expire because we don't want to keep them for forever. So we get more traffic in T4, and at the same time, the blue one expires, and here we go, we have a second ingress point. As an overview, that's pretty much how it goes. There are also rules for when to aggregate upwards. There are rules for when to throw away things, or when ingress points are not prevalent anymore, when they age out, don't see enough samples, or get the wrong samples that we can't really say anymore that this is a correct ingress point. For any further information on this, I will refer you to the paper, just for the sense that I don't want to go over time. And we implemented all of this, and we implemented all of this, I think, 7 or 8 years ago. And in the end, for the research paper, we did a parameter study on actually figuring out which parameters would be the best to set, and where do we get the most stable results fastest. And we got to the point that anything below /28 only really increases RAM, but doesn't give more accuracy. A 5% error margin is a good thing, although 10% or 2% doesn't really make a difference since the ingress points are fairly stable. and a rotation of 60 seconds. So meaning every 60 seconds we update from the data that we've gotten. We can actually react quite fast. Again, if you're interested in the complete parameter study, I will refer you to the paper. We actually did almost all of the combinations, I think. Okay, coming to the hardware requirements, we ran all of this. We have now been running this for this is from mid last year. It was 6 years then, now it's 7 years. We've been running this for over 6 years at a tier 1 ISP. We've been running this with tons of flows, tons of routers, and all of this is off-the-shelf commodity server by now, at least 7 years old. It hasn't been upgraded since then. It needs about 30 cores, 120 G of RAM, and it just goes on and detects the ingress points. Okay, few more words about the accuracy and what we actually see. So this is the, there are two curves here. On the left side, you see the relative traffic of an average day in the network. That is wrong. On the left side is the accuracy on the ingress point. On the right side is the traffic going from 1.0, which means that the network was fully loaded, down to almost below 0.2, which means only 20% of the traffic compared to the peak. On the left side is the ratio of how many of the ingress points we actually, or how much of the traffic we could actually attribute to an ingress point. And we see that during the night when the traffic is really low, our accuracy drops a little bit down to 88%. But on average, 92% of the traffic can be attributed to ingress links. And this does not take into account if this is high traffic or low traffic. It just says 92% of the traffic we can actually attribute. If we're looking into a more diverse view, so now what was added here is the top 5 and the top 20 based on volume. So we took the top 5 ASs that sent in traffic and the top 20 ASs that send in traffic. The accuracy especially for the heavy hitters increases to over 98% of the traffic being attributed to a single link that will, as I said, also update dynamically. Okay. The second thing, and this goes back to the fact that we don't use BGP, we looked at path asymmetries. So where does the ingress point not match what we could have or did glean from BGP? And the point here is, while for some ASs, like if you're looking at traffic that comes from a tier 1, the path asymmetry is fairly low. So over 90% of the traffic actually enters on the link where you also see a BGP announcement. The more traffic you're looking at, the less this is actually correlating. And if you're looking at the top 20, you're already at like only 70%, which means 30% of the time you might be at it not looking at the right ingress link. And if you're looking over all traffic, you're barely making the 50%. So the path asymmetry does exist, and it's actually a thing. So again, don't use BGP for this. Finally, we looked at the split that the IPD does compared to BGP. Now, keep in mind, we're looking at IPv4 here. This scheme, as I explained it, works the same way for IPv6. Of course, you won't have a /24 then. You'll have higher subnets, but it does work for IPv6 as well. And what you can clearly see in this is the cutoff for IPv4 at /24. Nothing goes below that. That's the gray bar, by the way, and careful, that one is cut off in the middle, so that's actually over 50% of the announcements are on a /24 level. Whereas if you're looking at the ingress point detection and you're looking at what subnet sizes that one's actually classifying, you can see that this goes down to /28, and it probably would have gone down lower if we had allowed it to, but that was our cutoff. Which means there is a lot more dynamic than you can see in the than you can see in BGP when you're actually looking at the traffic and attributing that to link and how the traffic is coming in. Yes. Okay. Finally, from our operational experience, like I said at the start, we use this tool for network troubleshooting. We use this tool for CDN ISP collaboration, mapping customers to traffic, optimizing traffic. And it also helps if you know what's going on and know where things are coming in to figure out those people that you actually need to talk to get problems solved. And again, router level balancing is not something that we solved, but luckily we didn't need to in the networks that we've been running this for now. And this concludes my talk. And I'm happy to take questions.
Questions from the audience? Alex, anything online? Good.
Go ahead. John Christoph with UIC and dataplane.org. So I'm curious if there's any impact or anything that you would do with any traffic sources or destinations whose addresses may be ambiguous or private address space or bogus. Does that even, is it even consequential enough to even worry about, I guess?
So one of the first things when we turned this on is I checked if I can see the multicast block. There shouldn't be any traffic in the multicast block, and as such, since you have this sort of split down when traffic's being classified, the multicast block needs to stay empty for me to actually see that worked, and that's actually the case. I did have that slide somewhere, but I don't think I have it here right now. So the multicast block stays empty or mostly empty. There's always some stuff flying around. What surprised me though is when we first turned this on, is that the 192.168/16, which is normally an RFC 1980 block, which shouldn't be used on the internet, that one was classified, and that one was clearly classified to a link that goes to a neighbor. Turns out they had a route leakage of their internal network and were actually ingressing traffic to the network that we were in and we were doing this for. Enabled us to talk to them and tell them, hey, stop sending us this, stop sending this traffic. The border router was nicely dropping it, but it did overload, it did load their link quite a bit. I hope that answers your question.
Next question, Alex.
Okay, Lowell Switzer, no affiliation. How did you arrive at 11 samples as the requirement?
That's just for the example. In the real world, this is a lot higher. We're actually using a quadratic function that I think for the /0 we have something like 2 or 3 million samples that we needed. Something that you can actually take a good decision on. The 11 here was only chosen for the example since I did not want to build an animation that puts a few million packets on the slide. So sorry for that. I should have said that before.
Makes sense to me. Any other questions from the floor? Going twice, going 3 times. Let's give Ingram a very warm thank you for his presentation and for the data. Ingmar, we will talk to you soon, and please present again. We like the stuff you come up with, so please continue that. Take care.
Thank you.